The Pythagorean theorem. It has over 300 proofs, and one of them uses trigonometry. It goes something like this. You use the cos square plus sin square equal to 1 formula, and then by plugging in their values, you prove that a plus b square is equal to c. But from where did we get this equation? Its proof in itself creates a circular loophole, as you will see over here, that we commonly learn in high school. As you can see, we get a square plus b square divided by c square, and then by Pythagorean theorem itself, we substitute in c square over there. That's the circular logic part. But is there another way to prove sine square plus cos square is equal to 1? There is, but surprisingly, it's not geometry dependent. We can derive it with continuous compounding. So, the formula that you see here is the classic compound interest formula. To get e, the fraction and the exponent must be the exact opposite. So, let's convert our fraction to 1 by x is equal to r by n. And now, what we get is basically the formula for e to the power r. As you can see over here, p of e to the power r is our final result. Now let's expand our formula via binomial theorem. Over here a is 1 and b is x by n. We expand it and we get an infinite series. However, there's a problem. We have factors like n of n minus 1 divided by n square. So what do we do about them? As n approaches infinity, these factors get reduced to 1 and we get a final clean formula. What makes e so special? Let's take a look at this graph. Over here, y is equal to e to the power of x. Over here, x is the rate of change as we saw earlier. But there is something else as well. Over here, the current value of e is the exact slope of e. If you know anything about slope, it's basically the rate of change. It's its own derivative. There is something else as well. What happens when you multiply a number with a negative counterpart? It just simply turns 180 degrees. What if we only rotate halfway? And that's exactly what imaginary numbers do. They rotate a number halfway, and then when you multiply it by again, you turn a complete 180 degrees. So I is basically like a command that forces you to turn by 90 degrees. Now we have a number z, which is equal to e to the power x. We multiply z with I, it turns by 90 degrees, meaning e to the power x is also multiplied with I. So what is the rate of change? It's by I itself, which gives us e to the power ix. Now let's expand our formula. Over here x is replaced with theta, and now by seeing the behavior of I in even powers, we get our formula split in two parts. The real part is cos and the imaginary part is sine. Let's take a look at our formula again. Previously, we replaced x with theta. But what is x? Length of one step in our compound interest is x by n, and we do that n amount of times. We get our final distance as x itself. So over here, x is the distance traveled on the curve formed. Now, the next question is, what is this curve and how does it form? To understand the formation of the arc, let's look at our e to the power ix. Over here, cos is negative and sine is positive. So when the tip of that line z is equal to the e to the power ix, first we go by sine and then we switch back to cos, which here is negative. So we go a bit back on the real part and then we end up at the sine imaginary part again. So we go up again. So this continuously forms a circular shape, as you can see over here. These points, sine and cos, constantly move to form a circle. Space-time tell matter how to move. Matter tells space-time how to curve. It's a quote in general relativity. Something similar happens over here as well. E to the power ix. E to the power I is the engine that tells x how to curve, and x tells the engine how far to move. Let's see it all play and connecting it to pi. As x becomes the value of pi, e to the power I pi becomes exactly minus 1. Upon transferring it on the other side, we get the most beautiful equation in all of mathematics. Now let's derive the main formula, e to the power minus ix. Let's expand it, and then the even powers in cos crush the negative sign, hence cos stays the same. However, in sine, where the power is odd, the minus x gets carried forward and each sign gets flipped. Hence, sign becomes negative. Now we have e to the power ix and e to the power minus ix. Let's multiply them. We get our final formula upon further simplification. Cos square x plus sine square x is really equal to 1. Now, how do we tie all of this together? From our previous formula, we can see that 1 is just equal to 1 squared. Meaning when we replace 1 with some constant c greater or less than 1, it affects the whole equation entirely. Meaning c is just a scaling factor. Over here, if we take a and b as the respective sides, we get the Pythagorean theorem. Now, the question is, why does sine stay the same no matter in which triangle? As we can see, opposite is equal to c times sine of x, and then upon further simplification, we get sine of x is equal to sine of x. But c over here is the hypotenuse, meaning opposite by hypotenuse is equal to sine. Now we are nearing the end of the video. Trigonometry is in the study of triangles. Triangles are, in a way, just a 2D shadow of something deeper that goes underneath. The rotation in the complex plane. And it's guided by this one formula over here. If this channel changed how you see math, consider subscribing. And I'll see you in another video.